Hi all, today's topic is error analysis. What do you mean by error? Error is the difference between the desired output and the actual output. The desired output is the reference input. If there is a difference between this desired output and the actual output, then the performance of the system is not satisfactory. The performance of the system is not up to the desired level. So our aim is to minimize the error. That means the difference between the desired output and the actual output. And what do you mean by steady state error? Steady state error is the error when time t tends to infinity. This steady state error reflects the accuracy of the system. There are many reasons for this error, that is the presence of nonlinearities in the system and imperfections in the system components, and sometimes the input to the system, uh, the input signal to the system will be a random signal. The signal is random in nature. In all for Because of all these reasons, there may be error in a system. Uh, and control systems may be classified according to their ability to follow step, ramp, and parabolic inputs. These are the standard inputs. Actual input may be considered as combination of such inputs. Before going into detail, we have to familiarize with some terms, that is type of a system. Consider an open loop transfer function in this form. G of s h of s is equal to k into TAS plus 1 into TBS plus 1 etc. divided by s raised to n into T1 of T1s plus 1 into T2s plus 1 etc. This n represents the type of the system. S raised to n means it represents a pole multiplicity at the origin. That means there will be n poles at the origin. A system is called type 0 if n is equal to 0. A system is called type 1 system if n is equal to 1, etc. And as the type number is increased, accuracy is improved. Remember this, as the type number is increased, accuracy is improved. We can prove this later. As the type number is increased, accuracy is improved. And in order to determine the accuracy of the system, we have to study some error constants. It is known as static error constants. There are three types of error constants: static position error constant, static velocity error constant, and static acceleration error constants. For static position error constant, the input is step input. Static velocity, the input will be ramp, and static acceleration error constant, the input is parabolic. Consider a feedback control system shown in this figure. The error signal E of s is given by R of s minus H of s C of s. E of s is equal to R of s minus this signal. This signal is C of s into H of s by the definition of transfer function. Now C of s is equal to E of s G of s. Therefore, E of s is equal to R of s minus H of s into G of s E of s. Or take this term to left hand side. So ES is equal to R of s divided by 1 plus GS HS. Remember this expression. Now applying the final value theorem. Steady state error is represented like this, equal to limit s tends to 0 s E of s is equal to limit s tends to 0 s R of s divided by 1 plus GS HS. So the expression for steady state error is limit s tends to 0 s R of s divided by 1 plus G of s H of s. remember this expression also. This is by applying final value theorem. What is final value theorem? If the given function is f of t, limit t tends to infinity f of t, that is the final value, is equal to limit s tends to 0 s f of s. Here e of s, steady state error. So steady state error is equal to limit s tends to 0 s e of s is equal to limit s tends to 0 s r of s divided by 1 plus gs hs. In a given system, the inputs may be position, velocity, pressure, temperature, etc. Now, static position error coefficient Kp. There are three error coefficients: static error coefficient, static position error coefficient, static velocity error coefficient, static acceleration error coefficient. First, we can see static position error coefficient, and it is denoted by Kp. Here, the input is unit step input. Therefore, R of s is equal to 1 by s. Now, steady state error ESS is equal to limit s tends to 0 s R of s divided by 1 plus GSHS. That is equal to limit s tends to 0 s divided by 1 plus GSHS into 1 by s, because R of s is equal to 1 by s. Now we define static position error coefficient Kp is equal to limit s tends to 0 G of s H of s. So applying the limit s tends to 0, Kp is equal to G0, G0, H0. So therefore steady state error is equal to this s, they will get cancelled. So 1 divided by 1 plus Kp. For type 0, Kp is equal to limit s tends to 0, G of s, H of s. Now, G of s, H of s is equal to K into TAS plus 1 into TBS plus 1 divided by s raised to n. T1s plus 1 into T2s plus 1, etc. Therefore, Kp is equal to limit s tends to 0, G of s, H of s is equal to this term. Applying the limit s tends to 0, this is equal to K. Therefore, steady state error ESS is equal to 1 divided by 1 plus Kp is equal to K, therefore is equal to 1 by 1 plus K. For type 1, then s raised to 1. Applying the limit s tends to 0, then Kp is equal to infinite value. Therefore, Es is equal to 0. So, what about the steady state error? When for type 0, there is a finite amount of error, that is 1 by 1 plus K. For type 0, there is a finite amount of steady state error, that's equal to 1 by 1 plus K. For type 1 and higher, there is no steady state error. That means as the type number is increased, accuracy is improved. So we proved that statement. As the type number is increased, accuracy is improved. For type 0, there is a finite amount of error. For type 1 and higher, there is no error. Next, static velocity error coefficient denoted by Kv. Here the input is ramp input, therefore R of s is equal to 1 by s square. Similar steps, steady state error is equal to limit s tends to 0 s R of s divided by 1 plus GSHS. Limit s tends to 0 s divided by 1 plus GSHS into 1 by s square, because ramp input R of s is equal to 1 by s square. Therefore, ES is equal to limit s tends to 0, 1 divided by s GSHS. This s, it will get cancelled. 1 s will get cancelled, then s plus SGSHS. Applying the limit s tends to 0, steady state error is equal to limit s tends to 0, 1 divided by SGSHS. Now define static velocity error coefficient Kv is equal to limit s tends to 0, Sg of s, H of s. Therefore, steady state error is equal to 1 by Kv. Kp, from the previous slide, Kp is equal to limit s tends to 0, G of s, H of s. Here, Kv is equal to limit s tends to 0, S, G of s, H of s. and steady state error is 1 by kV. For the here steady state error is 1 by 1 plus K2. Here 1 by K. For type 0, Kv is equal to limit s tends to 0 s g of s h of s by definition. That is equal to limit s tends to 0, substitute for g of s h of s. So this is equal to 0. S raised to 0, that's 1 s. So this is equal to 0. Therefore es is equal to infinite. For type 1, kv is equal to limit s tends to 0 s g of s h of s. That's equal to limit s tends to 0, this term, that's equal to k, because these two s, they will get cancelled. So this is equal to k. Therefore es steady state error is equal to 1 by k. There will be a finite amount of steady state error. For type 2 and higher, here in the denominator there will be s. Therefore kv is equal to infinite value. Therefore steady state error is equal to 0. Again, we can say that as the type number is increased, accuracy is improved. For type 0, infinite amount of steady state error. For type 1, finite amount of steady state error, and type 2 and higher, there is no steady state error. Therefore, as the type number is increased, accuracy is improved. Similarly, static acceleration error coefficient Ka, input is parabolic input, R of s is equal to 1 by s cube. Es is equal to limit s tends to 0 s R of s divided by 1 plus dshs. That's equal to limit s tends to 0 s divided by 1 plus dshs into 1 by s cube. Therefore, es is equal to limit s tends to 0 1 by s square g of s h of s. Now again, in a similar way, we have to define static acceleration error coefficient Ka is equal to limit s tends to 0 s square g of s h of s. Therefore, es is equal to 1 by Ka. For type 0, Ka is equal to limit s tends to 0 s square g of s h of s. Substitute for g of s h of s. This is equal to 0. Therefore, es is equal to 1 by the infinite. For type 1, again, substitute for g of s h of s. Therefore, Ka is equal to 0. Therefore, es is equal to infinite. For type 2, this square, these two terms will get cancelled. So k. Therefore, es is equal to 1 by k. There is a finite amount of error. For type 3 and higher, k applying the limit as s tends to 0, k is equal to infinite. Therefore, es is equal to 0. So again, as the type number is increased, accuracy is improved. For type 0 and type 1, infinite steady state error. For type 2, finite amount of steady state error. For type 3 and higher, there is no steady state error. And the results are tabulated here. In this table, the values for Kp, Kv and Ka. And in this table, the steady state error for unit step, unit ramp and unit parabolic. One problem. For a unity feedback control system, the open loop transfer function g of s is equal to 10 into s plus 2 divided by s square into s plus 1. Find the position, velocity and acceleration error constants. Unity feedback system, therefore h of s is equal to 1, kp is equal to limit s tends to 0, g of s h of s. That's equal to limit s tends to 0, g of s. That's equal to infinite. Therefore, steady state error is equal to 1 by 1 plus kp, that's equal to 0. Similarly, velocity error constant kv is equal to limit s tends to 0, s g of s h of s is equal to, substitute for g of s h of s, that's again equal to infinite. Therefore, steady state error is 1 by kv is equal to 0. Acceleration error constant Ka is equal to limit s tends to 0, s square g of s h of s. Substitute that is equal to 20. K is equal to 20. Therefore, steady state error is equal to reciprocal of this Ka. Thank you.